Okay, so in this video, we want to give an intuitive geometric presentation of the classical mean value theorem of differentiation. The statement is the following. If we have a function f of x that is continuous on the closed interval from a to b, where a and b are real numbers, and where f is also differentiable on the open interval, then there exists a number c between a and b such that f of b minus f of a over b minus a, that is the average slope of the function f on the interval from a to b, is equal to f prime of f at c, which is the instantaneous slope of the function at the point c. And if we look at this problem geometrically, you will see why this is very intuitive. So let's sketch a graph of an arbitrary function on an interval from a to b. Again, the assumption is on this interval the function is continuous and differentiable on the open interval. Say the function looks like this. So this is the point a f of a. This is the point b f of b. And now let's look at these two quantities geometrically. Right? If we draw the line connecting the point AF of A, BF of B, so connect these points with a line, you can ask, well, what is the slope of this line, right? Well, the slope is the total change in y over the change in x. The change in y of this line is simply f of b minus f of a. The change in x is b minus a. And so you see all this is the slope of the line connecting the points AF of A, BF of B, and that is what is known as the average slope of the function f on the interval from A to B. So let me just squeeze that in here. The slope of this line is the average slope of the function, which is the left-hand side of this equality, f of b minus f of a, total change in y of the function f on the interval from a to b over the total change in x, b minus a. And now f prime, again, is the derivative of the function that is geometrically the slope of the tangent line. So what the result says is that there must be at least one point in between a and b when the instantaneous slope of the function at c, the slope of its tangent line, is equal to its average slope on the interval. And if you look at the graph of the function, can you see at least a point where the tangent line would have the same slope as this line, right? And let me take a slightly thinner pen. You can see over here the slope of the tangent line is much larger than the slope of this line, but if you keep moving towards the right, the slope decreases until you reach a point where clearly the lines will be parallel. So right here we would have a possible value of c. If I try to pick it somewhat decently, yep. So this point right here being c, so if you draw the tangent line, and trying to make it look good, this is the tangent line to the function f of x. I'll add this in here. This is y equals f of x. This is the graph of f of x. And at this point, chosen carefully, again geometrically, the slope of the tangent line, of course, is the derivative of the function at the point c. And so you see it's very intuitive, and you can try. Sketch the function f in any way you want, and then move the tangent line along the function, and eventually you will reach a point when the slope of the tangent line will be the same as the slope of this line, which means geometrically the lines will be parallel. And in this case, there's a second value of c, right? If you keep increasing the x values, well, the tangent line now is no longer parallel as you move along the curve to the dotted line, but as you keep increasing x, there will be another point where the tangent line will be parallel to the dotted line. So where the exact slope of the function will be equal to the slope, the average slope of the function on the interval. So there's at least one c, there could be many. In this particular case there are two, there could be 3, 4, 5, and so on. But you see that this result is very intuitive when looked at geometrically. As long as the function is smooth, differentiable on the interval, then there will be at least one point on the function where its tangent line is parallel to the line connecting both endpoints in terms of slopes, where the average slope of the function is equal to its instantaneous slope. And that is the mean value theorem. Proving this rigorously is a bit more work, but again, here the objective is to make this result as intuitive as possible, and this is of course done geometrically.